everyone. Hope everyone's doing okay. So today we're going to talk about finally getting to DFT analysis. So we've talked about CFT. We've talked about basically these concepts in DFT of signal aliasing and spectral leakage. And now we're finally getting into how do we actually calculate a discrete Fourier transform. So we're going to focus on that today. And before we get started, actually, let me erase this. Let's just kind of review some of the concepts that we talked a little bit about in that signal aliasing and spectral leakage kind of little mini lecture there. So remember, we had some key definitions last time. So we said that our period t is going to be equal to n times delta t. So again, we're taking discrete points. We do not know the functional form of our original signal. We could also said that our sampling frequency, SFS, is going to be 1 over delta t. Our lowest frequency, this delta f, is going to be, as usual, 1 over t. We could rewrite that as 1 over n delta t. And we could also rewrite that as fs over n. So all these equations we really need to kind of start to know by heart and have no question kind of ripping those out whenever we kind of need to utilize that. So start working on that, get those all memorized and ready to go. So how do we actually get to calculating a discrete Fourier transform? So we are going to kind of do that right now. Let me erase this now that you have those kind of key equations that we need to have in the back of our pockets. So it all comes down again to calculating those harmonic coefficients. So for our, let me scroll down a little bit here. When we had our continuous Fourier transform, we could calculate a sub n was 2 over t, 0 to t. We took the integral because we knew the functional form of this equation, cosine of 2 pi n time over t dt. Now, we could take the integral here because we knew that y of t was 10x or 5 or whatever, we knew the functional form of this equation. With a discrete Fourier transform, we do not know that. Just as we saw last time, we're going to have some kind of signal here that we get, and we're going to pull out points discretely at some specific sampling frequency. So we don't really know what the functional form of this equation is. Instead, we're going to kind of analyze these points. So if we can't take the integral, the way we're going to calculate these harmonic coefficients is transform it into a sum. So we already luckily have some of the key equations that we're going to need in order to kind of transfer and kind of rewrite how to calculate this a sub n. So we already know that t, we're going to rewrite this as n delta t. Time, we're going to grab specific time intervals. So time at any kind of given integer value r, so we're instead of summing over little n, our harmonic coefficients, we're going to introduce kind of this new parameter r. So again, you could kind of, because we don't want to confuse it with, again, we're going to take discrete samples, but we need to kind of maintain our harmonic coefficients. So we're just going to introduce this kind of term r here. So nothing crazy, but time at any given r value, and we're going to see what that is in a second when we have an actual example to do, is going to be just r times the number of basically discrete points times delta t. So we are just going to substitute that back in here, and that's all this equation does here. So let's just rewrite it and see if we get this exact expression. So rewriting this term and substituting in, getting rid of those integrals and substituting it with summations. So a sub n, I'm going to replace t with n delta t. I'm going to now sum from r equals to 1 to n, and I'm going to have y, I'm going to replace t with t of r, because we're going to grab basically discrete y values at given intervals r. So one way you can kind of think about that or visualize that is, let's look at our original signal, y of t. It's just these kind of like, again, these series of points here, 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 here. This value is the first, essentially, data point that we have. So that's r equals 1. This is r equals 2, 3, 4, 5, etc. So you're just taking, basically, this list of points is 10, 12, 15. That is our, so this is our data point. This is our y value. Our r value is just, we're grabbing the first data point. So this is 1, 2, 3, etc., etc., as you can kind of see here. 3, 4, exactly. So let me erase that. So that is just what we're going to be talking about right here. I am going to finish writing this expression to make it a little bit nicer. So keep substituting it in. So cosine now becomes 2 pi. That remains the same. Same thing with n. T is n delta t. Substituting that in. I'm going to run out of space as usual, but luckily I think I have just a little bit more room. Oh, nice. This is the benefit of one of the few benefits of online teaching. The whiteboard, I would have been in big trouble. I'm going to replace t with this here. So r times your delta t, and dt is just going to be delta t. So some things are going to cancel out here, and then we're also going to cancel out here, and that's it. So we get this nice expression here. That is going to be how we are going to calculate our harmonic coefficients. So that's it. And as you're going to see here in a second, this is actually a really kind of powerful statement. We're going to actually work and see why this is the case in a second. But why do we only go to n over 2 points? Well, one reason, if you look at the Mathematica notebook that I've kind of posted on Canvas already, you'll see that it's actually the harmonic coefficients are mirror images of each other past this n over 2. So once you get past n over 2, there's this mirror symmetry. And actually, we'll show that in kind of a later video when we kind of do some more worked examples. But there is another reason. So mirror symmetry is one of them. But we remember from last time that discussion of basically signal aliasing that on our frequency spectrum, our last point here is this n over 2 delta f. Because we know that delta f is fs over n. This n over 2 denotes kind of your, what frequency is that? The highest frequency we can resolve once we pick an fs. We saw that f Nyquist was equal to fs over 2. Once we plug that in here, the n's cancel, and you're left with fs over 2. So the Nyquist frequency. So that's why we only go to n over 2. And we only go to n over 2 minus 1 because what happens if we plug in for n over 2 in a sine? So if we have sine of 2 pi r n over 2 n, these cancel, this cancels, this cancels, this cancels. What is sine times pi of any integer value? 0. So that's why we don't even bother to go to n over 2 here, because that bn is going to be 0. So again, that's just math. You could always calculate it out, but again, it's going to save you some time when you come to an exam. So that's all the adjustment we make. We went from basically CFT, where we had, let me scroll up here just a little bit to remind ourselves. We went from integrals here in our CFT to summations right here. And this is how we're going to solve all the rest of our we're going to generate our frequency spectrum just like we did last time. Everything else remains the same. All the hard work's done. So now let's get to the fun part and actually calculate some discrete Fourier transforms. And hopefully you like math, because there's going to be a lot of it. The same thing holds true for, again, our discrete Fourier transform, or your Fourier series as well. So once you have your harmonic coefficients, you're good to go. Now, this is kind of the expression that we've been working with kind of previously. Again, just rewriting our Fourier terms. You could kind of see that we could rewrite our discrete Fourier transform or our Fourier series with this kind of really nice, basically kind of really actually cool transformation. So if you kind of follow along the math here, again, this is the same math we've kind of introduced previously, we could rewrite this expression above and rewrite it in terms of delta f. So that's all this is math, is just rearranging essentially some values here. So nothing too crazy, but this is how we want to write our Fourier series. That is what I highly suggest when you're trying to calculate or you're trying to plot your calculated Fourier series, write in terms of this, because again, it shows you how if you're given a discrete Fourier transform, calculated Fourier series, you could calculate delta f very quickly just by looking essentially at these values. So I would absolutely use this if you're trying to plot your Fourier series. So this is a nice expression, but again, this gives you, the key difference here is it gives you this delta f. So we always want, delta f is a critical parameter. It tells us a lot about kind of our signal. We want to be able to kind of pull that out when we want. So let's do one quick, real quick example of how do you actually calculate a discrete Fourier transform. So let's look at the following signal that we have here. So right now, we are going to maybe go on to the next page. So this is my signal. So this is the graph kind of here. And then here, we're going to look down below. Those are going to be kind of the actual points that we're given. So how are we going to work with this sample? Well, what we're going to do is simply do essentially, calculate our Fourier series as usual. So what is our delta t, or what is our delta t, or what is our sampling frequency? Or let's first ask the question, is this signal periodic? Well, it's not periodic within this period, but again, it's aperiodic. But we could, again, we've talked about this previously in the class. You could deal with any signal, whether it's periodic or aperiodic, using discrete Fourier transforms. So you don't have to worry about that. So because it's not periodic within this period, well, our period is just going to be this entire 2 seconds. So this entire period, so 2 seconds. If our period is 2 seconds, what is our basically our sampling frequency? Well, actually, we'll deal with the sampling frequency in just a bit. So instead, what we're going to kind of calculate here is actually, well, if we know that this is basically 1.98, well, technically, 2 seconds is our period. We know that our delta F is going to be 1 over your period, which is equal to 1 over your n number of points times your delta t. So it's approximately 2 seconds. So what is our delta t here? Well, our delta t seems to be approximately, again, 0.11 seconds. So our sampling frequency we know is 1 over delta t. What is that going to be? Well, the sampling frequency is going to be approximately, again, 9,000 hertz. So again, this is just running through the math. You can kind of double check and calculate this on your own. And what is our number of points? Our n number of points is 18. So we've got all these kind of critical values, all just by looking essentially at this table, or this graph here, or this table below. So how can we have now, and you can calculate your delta F, which is just going to be 500 hertz, approximately. And again, oh, sorry, excuse me, this is in milliseconds. My mistake. And not 2 seconds, 2 milliseconds. Excuse my notation. So we have all our values. So we have capital T, we have our fundamental frequency, and now we could just work and solve the rest of this problem. So let's actually go about the business of calculating our harmonic coefficients. So let's give us some space over here, and actually we could see our expression right here. So we know that our period, our number of points n, is equal to 18, as we just saw above here. What else do we know in this problem? That's really kind of all we need to do to start calculating our harmonic coefficients. So what we're going to do, if I want to calculate the first harmonic coefficients, I'm going to have to sum. So a sub 1 equals 2 over 18. Now, here's going to be the annoying part. We have to sum from r equals 1 to n. So I am going to multiply this. What is my first y value data point? Well, it's 10 volts, as you can see up there. So at this first value here, let me kind of draw here. This, again, is r equals 1, 2, 3, 4, 5. So this is my first, oh, excuse me. Sorry about that. So this is my first data point right here. So it is going to go at 10. So my y value at r is equal to 1 is this 10 volts. So I'm going to go back down to here. So it is 10 volts times cosine of 2 pi. What is my r value here? 1 times what is my n value? It's already given here, 1 over 18. Plus, now you're going to see where this gets a little annoying. What is my y value at the second data point? I've erased, or I've written over it. It is 30. So plus, and you're going to see 30 times cosine of 2 pi times 2, because our R value has changed. We were taking the second data point there over 18. Still the first harmonic. Let me kind of clean that up. What is the next one? So we have to go, again, we're going to sum all the way to 18. I'm not going to do all of them, but you're going to get the picture here. So we've done 30. What's the third point? 70. So plus 70 times cosine of 2 pi. What is my R value here? First point, second point, third point, still times the first harmonic over 18. Plus, you can guess it. What's the fourth data point? 65. 65 times cosine of 2 pi times, what is this data point? Fourth, first harmonic, 18, and et cetera, et cetera, et cetera, et cetera. So you can see that we really want to hope for a periodic signal so we can reduce our math. But again, this is not aperiodic, so we need to kind of, again, this is we have to go all the way to 18, and this just calculates the first harmonic. To calculate the second harmonic, we would do the same thing, except now the only thing that would change would be 10 times cosine 2 pi times 1 times 2 over 18, plus 30 times cosine of 2 pi times 2 times 1 over, 2 times 2 over 18, because we're doing the second harmonic. So again, it gets a little bit nasty there, so we really just want, you want to be able to kind of work through this. I'm going to clean this up just a little bit. Let me rewrite that one just a second. So plus 30 times cosine of 2 pi times 2 times 2, because R is 2, N is 2, over 18, et cetera, et cetera, et cetera. So you have to do that for, again, how many number of harmonics that we have? You have to calculate 9 harmonics in this scenario. So that is a difficult situation to deal with. And again, that is why we use Mathematica or you use MATLAB. You write the code, you kind of want to basically spit out this equation quickly, because again, we want to get to our frequency spectrum where we can plot these delta Fs all the way to n over 2 delta F. So, yeah. And you could read through in the notes. Again, it kind of shows how to kind of do this and how to kind of calculate these values. So you can double check your answers that way. There's a lot that kind of goes on into here. I've also attached, and if people are interested, I'd be happy to provide the Mathematica notebook. I've already provided in Canvas, but if you want to, if you're watching this lecture and you want it, I'd be happy to try to include that or a link to it, because it gives you some nice examples, and you can always double check essentially your answer. So yeah, that's kind of the nuts and bolts of the discrete Fourier transform. And so again, it just changes depending on if it's periodic or not, but the process is exactly the same. So yeah, that's discrete Fourier transform in a nutshell. So if you have any questions, if you want more worked examples after going through these ones that are kind of highlighted in the notes, if you need to copy the notes, please let me know as well. I'd be happy to provide them. And yeah, that's it for kind of how to do the discrete Fourier transform. So let me know if there's any issues, if you need more worked examples, if there are any problems in the problem set that are giving you headaches, and I'd be happy to kind of do a little mini lecture and solve one of those if it's really giving you trouble. So be safe, have a great day, and yeah, I'll see you all next time, and we're going to get into mechanics, which is finally some material science topic, and you know that I love material science, so that is going to be a really fun lecture. So yeah, I'll see you all next time.